Hi everyone, I'm Titouan Carette, and I'm here to present joint work with Marc Devim and Simon Perdry. And what we did is to extend graphical languages to streams of qubits. So the global model is that usually you have some qubits, you have your diagrams, you apply it on your qubits, and you have some outputs. You have a one-shot model like this. What we do here, that we assume that we have a global clock, okay? And we will have a new kind of wires containing streams of qubits. And what's happening in a stream of qubits is that at tick 1, you receive a qubit, at tick 2, you receive a qubit, and you do this forever. So at each tick, you receive some qubits, you do some computation, and you output some other qubits. So we have different kind of wires. First, we have the iota wires. So the iota wires, this is just, you receive at tick 1 qubits, and you output another qubits, and nothing after. So if you have a gate, a iota gate is at tick 1, you receive a qubit, you apply the gate, you output the qubits, and then nothing will happen, okay, forever. You also have omega gates. So omega gates, you have an omega wire. So this is the wires for streams. And the stream is at each tick, you receive a qubit. So omega gate is at each tick, you receive qubits, you apply your gates, you have some outputs, you output them, and you do this forever at each tick. For those two families of gates, we also have delayed version. So the delay, we denote it with this diamond here. And then what is a delayed iota gate is that if you delay k time, it means that until tick k, nothing happens. At tick k, you will receive some qubits. You applied your gate, you output your qubits. And after that, nothing happens. You also have delayed omega gates. So if you delay an omega gates k time, what you obtain that until tick k, nothing happens. But starting from tick k, you will receive at each tick some qubits, apply your gate, and output the corresponding qubits. Okay, so those are the four kind of wires and gates that we will see in our language. And now we also need other gates to make them interact. So first we have those derivatives and initialization. So stream derivative, you see, you take an omega input, so a stream of qubits, and you will output a iota gate, a iota type. So just one qubit at tick 1 and nothing after, and a delay stream, which is delayed omega. So nothing at tick 1, but after you have one qubit at each tick. Okay. So in fact, you see those two gates, they are inverse of each other. So we have this rewriting rule. So if you know scalable notations, this is exactly the same rules because kind of scalable notation inspired. And this ensures, in fact, that those two types are isomorphic, you know, omega and iota tensor delayed omega. This is kind of the same thing operationally. And we also have these distribution rules ensuring, in fact, that if you have an omega gate, you can make it commute with triangles. And then you see that, in fact, an omega gate is equivalent to a iota gate and a delayed omega gate, okay? So applying something at each tick and applying something at tick 1, and then from tick 1, something at each tick is the same, okay? So for now, we only have, we are not able to have interaction with, between ticks, okay? We can say we apply the same thing at each tick, but what happened at ticks at k plus 1 can never depend on what happened at tick k, okay? So to make those ticks interact between each other, we will add a new generator. It's called the, and I promise it's the last one. It's called the delay gates. So what does a delay gate? So you see at tick 1, it receives a qubit and it outputs nothing, okay, because the output type is delayed omega. And at tick 2, it will receive another qubits, store it in the memory, and output the tick of the qubit of tick 1, okay, that was stored in the memory. So this delay gate is really acting like a memory, a delay. So you receive some qubits and you will wait one tick before releasing them. And from this delay gate, we can start building interesting diagrams. So let's focus on these diagrams here on the left. So you see you have a CNOT gate. And here you have a ket 0. This ket 0 is a iota type. Okay, so just ket 0 at tick 1, and after it's nothing. And then what you do is that at tick 1, you use this ket 0 as a control, And you also have an input. So all the other wires are omega or delayed omega. You receive a qubit at tick 1 like this. So you would apply the C naught on ket 0 and your input. And then you have two inputs. The first one, you will just output it at tick 1, okay? But the second one, you will store it in the memory. So here we use this feedback loop. So we have a feedback loop, but feedback loops are only allowed if you put a delay on them. It's called delay traces. So you have this feedback loop, so you store it in the memory, and then at tick 2, what you will do is reuse this qubit in the memory as a control for the next input you will receive, okay? And you do this forever, forever, forever. So if you unfold this diagram, you obtain what we have on the right here. This is a cascade of C naught. So you see forever, you always use the previously computed qubits to control the next one. Okay, so this is for the kind of things we can do, what the graphical language looks like. Now, what kind of semantics can we give to such languages? So we have two options. First idea is to say, if you look just at TK, this is just usual quantum computation, everything finite. So this is just a quantum circuit, so the X diagram. But we need to divide inputs into two families, two categories, let's say from outputs. First, we have the present inputs that we really receive at tick K. But also, we have some past inputs that are in fact the qubits stored previously in the memory. Okay, so we have two kinds of inputs. And this is the same for outputs. We have the present outputs, the one that we will output at tick K, at the present tick. And we also have the future outputs, which are things that we will store in the memory for the next ticks. Okay, so you have, for each tick, you have one quantum circuit, okay, with those inputs and outputs. And this is what we call the stateful sequence corresponding to your diagram. So this is an infinite family of usual circuits. And if you want to get an idea of what the infinite circuits look like, you can just plug, each time you will plug the future outputs of TK into the past inputs of TK plus 1. And then you can build your infinite circuits like this. So this is the stateful sequence interpretation. And this corresponds, in fact, exactly to our diagrams, to our circuits. But the problem is that in real life, this is not what happens. In real life, what we do is that we start a computation, and at some point, let's say tick K, we say, okay, we stop the computation here, let's see what we got. So what do we have is we have all the qubits computed for now, okay, and we need to trace out what is in the memory, okay? So we need to erase the stored qubits. We will never see them, okay? This is the end. So this gives us also another sequence of circuits. We call them the finite approximations, okay? And this finite approximation, that corresponds to reality. This is what we are really interested in, in fact. So the question is, are those two points of view equivalent? And not exactly. First, if we start from the stateful sequence, we see it's easy to compute the finite approximations. We just cut we choose the right layer, and then you just plug a ground, a discard map. So we trace out the qubit, the memory, and we get finite approximation. But the reverse direction is not true. If I know the finite approximation, I'm not able to recover a unique stateful sequence for the following reasons. If we have a causal gate, trace preserving, so which is a side effect free gate, it's not possible if you have no access to the output to guess if the gate have been applied or not. Then we see here we have two stateful sequences, which are clearly different, because of the first one, you see you apply C before storing the memory, and on the second one, you apply C after taking the qubit from the memory. But on an operational point of view, from the point of view of finite approximation, you will never be able to make the difference between the two, okay? So we need to caution by this relation at least. Something else that can happen concerns idempotence. If you have a gate pi, which is an idempotent, so this time pi might have some side effects, but those side effects will also be idempotent. So you might tell if it happens or not, but you are not able to say if it happened once or twice. And again, we have two stateful sequences here that are different, okay, but impossible to differentiate on an operational point of view. For finite approximations, the finite approximations are the same. So we need to give corresponding rewriting rule to quotient like this, our diagrams. So those are the rewriting rule in question. So each time we have a causal gate, then we must allow it to commute with the delay trace, okay? We can send it to the future or to the past just by delaying. The same with idempotent. If we have an idempotent gate, you must be able to send a copy of you, a delayed copy of you to the future, because it doesn't matter. There is no difference. So are those commutations rules enough? In fact, no, because at some point we have no choice. We need to take into account infinity. So let's consider, for example, infinite storing. Here, so what's happening on the left? You see at tick 1, you receive 1 qubit and you store it in the memory. At tick 2, you take your qubit in the memory and you store it again. And you do this forever, okay? So from an operational point of view, you will never see this qubit again. It is hidden in the memory forever. So this must be equal to this discard map here, to tracing out the qubit from the start, okay? But we cannot show this equality using the rewriting rule I've shown you before. So we need to add something, which is a meta principle, a coinduction principle. So this coinduction principle says that if you have two diagrams, S and T, you want to show they are equal, then you have the right to assume for free that their delayed version are equal. So this might be counterintuitive to have some free hypothesis like this. A way to understand it, if one of your friends use this principle and you want to challenge it, you see, so they use this, so they manage using the axioms, the writing rules to show this by assuming that the delay version are good. So then the only thing you can attack is say, no, you don't have the right to use this hypothesis, okay? The delayed version are different. But now you're trapped, because if they manage to do it once, they can do it forever. They can apply the same rules, all delayed, to show that, in fact, they can show the delayed diagrams are equal by assuming that the delayed diagrams 2 times are equal, okay? And they can go like this forever. And you will just be able to say, okay, so far you are good, but I'm sure that at the infinity, it's wrong. But you will never be able to reach infinity, okay? So this is the point. If you are not able to show the difference between two diagrams in a finite number of steps, then you don't have the choice. You need to assume they are equal. So this is the point of this coinduction axiom. So in practice, how do we use it? Let's come back to infinite storing. So we start from the diagrams on the left, okay? And then we first use a distribution rule, okay? So we unfold one step of the diagram. So we end up with this. And here we see we recover exactly the same shape, the same diagram as before, but delayed one time in the future. So here we can apply the coinduction principle to say that this delayed diagram is equivalent to the delayed tracing out, the delayed discard map. And then the delayed discard map is causal. This is a trace preserving operator, side effect free. So we can use the commutation rule and make it go through the delay trace like this. And we end up with the usual discard map. Okay, and we managed to prove the infinite storing equality. So in fact, we're able to prove that we have completeness results. If two diagrams have the same finite approximation sequences, then you can, using only the rewriting rules and the coinduction principle, that they are equal. Okay, so we have a completeness like this. We have some kind of universality, but with very restricted kind of finite approximation sequences. Okay, so in fact, those are a little longer. It's a little long to explain. So I did some detail in this talk, but all the main ideas are there. And if you're interested, I really invite you to look at the paper that contains a lot more. Here, so we managed to represent finite memory quantum computing. So this is interesting, but this is still a very restricted model. Okay, there are not a lot that we can do. And we are now working on extending this kind of construction to unbounded memories. So this is a work in progress, and I hope you will see some of it soon. So thank you very much for your attention, and that's all for me.